In order to create our regression, we must start by declaring the inputs and targets. Our target is the log price. Therefore, we can simply write targets equals data preprocessed log price. Our inputs are data preprocessed without log price. Simple as that. Okay, let's scale our data. We've already seen how to do that with standard scalar. So let's first import it from sklearn preprocessing and then create a variable scalar, which will be an instance of the standard scalar class. Finally, we must fit the inputs using scalar.fit inputs. We use the transform method to get the standardized inputs. So, inputs scaled equals scalar transform inputs. And that's all. We have standardized all input variables. Note that it is not usually recommended to standardize dummy variables. In fact, many practitioners would argue strongly against it. For ML purposes, we rarely put too much thought into it and go with the scale dummies as scaling has no effect on their predictive power. Once scaled, though, they lose all their dummy meaning. In the practical example at the end of the logistic regression section, we will explore how to implement a custom scalar, which standardizes only the continuous variables while leaving the dummies unchanged. All right. Finally, let's split our data into training and testing. I'll import the train test split method from sklearn.modelSelection. Next, let xtrain, xtest, ytrain, and ytest be equal to train test split brackets. The first argument refers to the x's, so inputs scaled. The second argument refers to the y's, so targets. We'll set the test size to 0.2, so we've got an 80-20 split. And we'll also use a random state, so we can later fiddle with the model. Okay, we have created 4 new variables. These with the suffix train will be used to train the model, and those with the suffix test will be used to test it. A regression is created in the exact same way as we've done many times. Let reg be an instance of the linear regression class. Next, we fit the regression with the train inputs and train targets, contained in xtrain and ytrain respectively. As you know very well, this was enough to create a linear regression model. In fact, it is not simply a linear, but a log linear regression, as our dependent variable is the logarithm of price. Great job! A simple way to check the final result is to plot the predicted values of our regression against the observed values. The observed values are the targets. We can obtain the predicted values using reg.predict xtrain and store them in a variable called y-hat. As you may remember, the predictions of the linear model are labeled with y-hat, so it's only right to name the variable like this. Okay, let's create a scatterplot of y-train and y-hat, or the targets and the predictions. I'll also name the axes and limit them so they are comparable. In the best case scenario, if a target is 7, we want the prediction to be 7. If a target is 10, we want the prediction to be also 10. Ultimately, we can draw a 45-degree line which shows the best possible match between targets and predictions. The closer our scatterplot is to this line, the better the model. Our result is not perfect, but it's definitely not random. We can clearly see that the points are situated around the 45-degree line, so our model has passed this first check. So far, so good. Another popular check is the residual plot. The residuals are the differences between the targets and the predictions. A residual plot refers to the distribution of the residuals. So, we can simply use the SNS dist plot from several lectures ago and plot the difference between ytrain and y-hat. Here it is. From the regression assumptions, we know that the errors must be normally distributed with a mean of 0. The residuals are the estimates of the errors, so we would expect the same from them. The result looks quite normal in the sense of normally distributed. The mean seems to be 0 too. The only possible issue could be that there is a much longer tail on the negative side. Therefore, there are certain observations for which ytrain minus y-hat is much lower than the mean. This implies that those predictions tend to overestimate the targets. From the fact that there are no such observations on the right side, we conclude that the predictions rarely underestimate the targets. This is food for thought and can serve as a guidance on how to better our model. Okay, Finally, let's calculate the R-squared. Reg, score, of X-train and Y-train. The result is around 75%. Therefore, our model is explaining 75% of the variability of the data. This is a relatively good result. However, it certainly could be better, but that would be your homework at the end of the section. Before we move on, let's find the weights and bias. The bias was contained in reg intercept, while the weights in reg coef. Since the weights are hard to read in this way, we'll create a summary table with the feature names and the corresponding weights. Here it is. This model is far from interpretable. The dependent variable is a logarithm and all features are standardized, including the dummies. But let's work with what we've got. First, some weights are positives, others negative. A positive weight shows that as a feature increases in value, so do the log price and price. An example is engine volume. The bigger the engine volume, the higher the price. Alternatively, a negative weight shows that as a feature increases in value, the price of the car decreases. A prominent example is mileage. The more a car is being driven, the lower the price gets. The situation for dummies is a bit different. Since we dropped one category for each discrete variable, when all included dummies are 0, then the drop dummy is 1. Let's take brand, for instance. We'll quickly display all categories that used to exist using data cleaned, brand, unique. There were 7 brands: BMW, Mercedes, Audi, Toyota, Renault, Volkswagen, and Mitsubishi. By looking at the weights table, we realize that Audi was the dropped one. Therefore, whenever all other dummies are 0, Audi is 1. So, Audi is the benchmark. If another brand dummy is positive, it means that all else equal, the respective brand is more expensive than Audi. For instance, BMW's coefficient is positive, so on average, if a car is a BMW, it will be more expensive than an Audi. Similarly, if a car is Mitsubishi, it will be cheaper than an Audi. You will notice that the Mercedes weight is positive, but very close to 0. Since the dummies are scaled, we cannot be completely sure if a Mercedes is more expensive, but it seems to be as expensive as an Audi. Okay, we can think about the other dummies in a similar way. We display the possible categories and identify which one is the benchmark. I'll leave that for homework. Finally, the size of the weight is also important. We said that standardized weights are comparable, and that's why we standardized them. Clearly, mileage is the most prominent feature in this regression. It is more than twice as important as engine volume. It is also worth noting that it doesn't make sense to compare the continuous variables with the dummies. Dummies are compared with a benchmark dummy for the respective discrete variable, like we compared the brands with Audi. Okay, with this in mind, let's proceed to our final part of the example, testing. Thanks for watching.